Madam, shall I start now? 30 years, only 30.
Yeah.
Okay. Okay. So, good morning to everyone. I am Dr. Apul Narayan Dev, Associate Professor of Center for Applied Mathematics and Computing, Faculty of Engineering and Technology, ITER. Today, we are going to organize first departmental webinar under SOA Weekly Academic Lecture, SOAWAL, handed by Professor Dr. Nasiketa Sharma. Today's webinar topic is diving into application of fundamental analysis to partial differential equation. So we are proud enough for our Honorable President, Professor Dr. Manoranjan Nayak of Siksha Anusandhan deemed to be University for his constant inspiration, guidance, and encouragement for research activities, conducting international conferences, webinars, etc. So it is my great honor to welcome the HOD of Center for Applied Mathematics, Professor Dr. Manjula Das, and the of Mathematics, and all my senior professor, my colleagues, research scholar, and MSc student participating in this webinar on diving into application of fundamental functional analysis to partial differential equations. I am sure you are going to witness a wonderful academic discourse in the coming 1 hour. On this occasion, we have with us our respected guest, Dr. Debajyoti Choudhuri, Assistant Professor, Department of Mathematics, NIT Rourkela, Odisha. So I am now requesting to Dr. Abhijit Choudhuri to give a brief introduction about our speakers.
Thank you, Dr. Apul Dev. Please allow me to introduce the speaker of today's webinar, Dr. Debajyoti Choudhuri, who is an excellent academician. Dr. Choudhuri graduated in mathematics honors from Osmania University, postgraduated and completed his PhD in mathematics from University of Hyderabad. Later in 2012, Dr. Choudhuri had been visiting scholar of mathematics at the Center of Theoretical Studies and had been an NVCM fellow at IIT Kharagpur. Later, he served as an assistant professor in the Department of Mathematics at NIT Siksha for 1 year, and presently he is an assistant professor, grade 1, in the Department of Mathematics at NIT Rourkela. Dr. Choudhuri received professional grants in 2014 and EPSRC grant in 2018 for visiting as an academic advisor to the University of Edgbaston, and received professional development grant for visiting University of Aveiro, Portugal in 2016. He was awarded also ASCI fellowship as a visiting scientist to Aalto University in Finland. Dr. Choudhuri won the silver medal in regional Olympics, regional mathematics Olympics in 2002. Besides qualifying NET and GATE, he received fellowship from Clay Mathematics Institute at ETH Zurich in Switzerland in 2008, and was also awarded K.V. Rao Young Scientist Award in 2010. Dr. Choudhuri has published 27 research papers so far in reputed peer-reviewed journals. 2 PhD scholars are graduated already, and 1 PhD scholar has recently submitted her thesis. And under the supervision of Dr. Choudhuri, her name is Akashmita. She has joined recently Center for Applied Mathematics and Computing in our university. He has one CSIR research sponsored project and matrix project from ACRB, both of which are continuing. And Dr. Choudhuri presented papers and participated in several national and international conferences and workshops. He was recently invited as a speaker in an online workshop, WFANA 2021 at NIT Trichy. So now I request Dr. Choudhuri to deliver the talk for which we are eagerly waiting for. Thank you.
Thank you, Dr. Abhijit and Dr. Apuldev, for the kind introduction and the invitation. So firstly, let me check whether am I audible in a proper manner or not. Am I audible?
Yes, you are audible, Dr. Choudhuri.
Okay, thanks. So it's indeed a pleasure to reconnect with Dr. Abhijit, whom I have known for quite some time. And this time it's on an academic front. And I would like to congratulate him and his team for coming up with this concept of weekly webinar, which needs to be aped by many other institutes in the country. And not just that, their team has also thought of coming up with a compilation of all the lectures in the form of a volume. Okay, and as I'm told that this is probably the first lecture in the series to come.
Yes.
This is the first lecture, right? Yeah.
Yes.
Yeah.
Okay. So thanks again for the kind invitation. And so let me just get on with the proceedings. So I hope my screen is visible.
Yeah, it's visible.
Okay. So today I'll be speaking on certain applications, basically certain tools in functional analysis, which will be used to tackle the existence and multiplicity problems in PDEs, especially the elliptic PDEs. Okay, especially the elliptic PDEs. And towards this, I have chosen, this is more of an impromptu academic discourse. Okay, so this is not a prepared sort of lecture where I'll be having a slide or I'll roll slide after slide. So this is just going to be an impromptu discourse and will move along with the flow of the audience. Okay. So two problems which I have chosen for this particular inaugural lecture are as follows. One is a more cumbersome looking one. Just a second. Yeah. One is a more cumbersome looking problem. Okay. Omega, which is a subset of R3, okay, and which is a bounded domain, okay, which is a bounded domain, and on the boundary, which takes the value 0. Okay, so this is the boundary of the domain. Okay, that's my notation for the boundary of the domain omega. So you have something like this, some domain omega, and whose boundary is denoted by this. And this is, let's say, is sufficiently smooth. The question is how sufficient? We'll get along to know. Sufficiently smooth. Okay, because we require a certain degree of smoothness of the boundary to establish the existence of solution to the problem. And there are few other parameters which needs to be explained. Of course, I could have generalized it to a problem in n-dimensional space, but then let me just retain it to 3 dimensions. Okay. Now, the parameters lambda and mu are positive real numbers. Okay, they are just positive real numbers, and f is an L2 function. Okay, f is an L2 function. All right, so so this itself says that we are in for something really bizarre. Okay, because the moment you have an L2 function on the right hand side, you lose the pointwise agreement of the LHS and the RHS. Okay, so usually when you say that something is a solution to a PDE, let's say you want to find out the classical solution to a PDE of number 1, it should actually satisfy that this guy is equal to this quantity for every x in the domain. Okay, but that's not what we can do it right now, because f is an L2 function and elements of L2 space need not even be a function. Okay, so just a remark, just a passing remark here, that members, so let me know if my writing goes a bit illegible and my voice goes down during the course of the talk. Okay, members of the L2 space need not even be a function. So then how do we go for this? How do we go about this problem? How do we go about tackling this problem? So why it cannot be a function? Because, well, it could so be that this is an L2 function, right? So if you take this to be 0 everywhere, except at a point x0, okay, in omega, and just take it to be infinity at x equal to x0, then this is certainly an L2 function. This is a member of L2 space, but it fails to be a function, because at this space at this point we do not have a proper definition of it. Okay, so these are basically called as distributions or generalized functions. Okay, fine. So now we have lost the pointwise definition or the classical sense of definition. So we are deviating from the classical sense of a solution. We are now deviating from the classical sense of a solution. Okay. Okay, and this is what we will do. So what we will try to do is, firstly, we will first fix a solution space. Okay, because we are no more in the classical regime, because had it been a classical regime, I would have chosen my solution space to be C2 of omega, which is twice continuously differentiable functions, would have been a solution had it been a classical solution in the classical sense. But now I can no more choose this. Okay, I can no more choose this. So towards this, what I'll introduce you to is the Sobel of space. Okay, so this is where I'll introduce the audience to the notion of what is called as the Sobel of space. Okay, this was coined by Sergei Sobolov. The space was in around maybe so probably around the pre-war days. Okay, Sergei Sobolov, who was basically a physicist. Okay, so, and this was the era when the notions of functional analysis was still under construction, and we still did not have the notion of completeness at the disposal of mathematicians, let alone the physicists. So it was just when that Banach gave his famous completion theorem, which says that if you have an incomplete nonlinear space, then you can always find or construct a larger space in which this incomplete space sits inside this larger space as a dense subset. Okay, as a dense subset, and this larger space is actually the completion of this incomplete space. Okay, so the tool which was used by Sobolov to construct Sobel of space was the completion theorem which was proposed by Banach. Okay. Okay. So, and what was the go-to? This is a common practice. This is a common practice in functional analysis, that we choose the space C0 infinity. Okay, we choose the space C0 infinity as our incomplete space. Okay, because this is a rich class of space. Okay, so this consists of all those functions u from omega to r, real valued functions from omega to r, such that u is infinitely differentiable infinitely differentiable, and U on the boundary vanishes. Okay, so you can see that the space now has some kind of requirement which the PDE also requires. So we can find a common interest between functional and a PDE. Okay, the space itself has that structure inside, built-in structure inside that inside the space. Yeah. So this space, incidentally, is not complete with respect to any norm, and that's one very fundamental and strong result which was developed during that era, that the space of smooth functions which vanishes on the boundary fails to be complete with respect to any norm. Okay, so this has always been a go-to space whenever one constructs a new space. No matter whatever new space one comes up with, even to this date, the go-to space, the go-to incomplete norm space which a mathematician takes up is this C0 infinity space. So in order to complete this, so the norm which was chosen by Sobolov, is the following. So I have used the word, the symbol U for the unknown. So let me use the symbol V here. Okay, let me use the symbol V here. Okay, because I have already used U for the solution of the PDE. So the norm which was used here was, sorry, I'm extremely habituated in writing U for everything. So this guy alongside this guy with this. So this is the norm with which it was found that this space is incomplete. Well, of course, this is incomplete with any norm. So this is just a particular norm. And by the completion theorem, a completion of Y is with respect to the norm. This is my notation for the Sobel of norm. With respect to the norm, this is the Sobel of space. Right. So this is what is a Sobel of space, and it's denoted as W12. Okay, I'll explain what is 1 and 2 for. It tells you that the first derivative belongs to L2. That's what it means. Okay, so this is just the solution space which we will be requiring in this talk. So that is why I'm introducing you only to this Sobel of space. Of course, Sobel of space can be generalized to WKP, where the kth derivative belongs to LP, but that's not what I'm dealing with right now. So this consists of all those elements in the L2 space. Now here comes a bit of surprise. So you have all those L2 functions such that your gradient of U belongs to L2 cube. Now one may ask that L2 itself is not a function, so forget about its derivative. It is, firstly, it may not even be a function. So how am I even constructing, even thinking of talking about the gradient of a function in L2 space? And this is where this is when the notion of weak derivatives was coined. Okay, this is when the notion of weak derivatives was coined. So it's not just, so just imagine that just a change in the parameter f, just a change in the given data f led to the formation of so many tools in functional analysis. Okay, it not only led to the construction of a space, but also it led to the construction of a notion of derivative, a new notion of derivative to fit into the scheme of things. Okay, to fit into the scheme of things. So so we say that, so let me give a formal definition of weak derivative. So it's a sort of crash course, so I'm not going to merge in details into it. So a function, let me put a function in quotes, a function phi, or let's say W, is a weak derivative of V if V belongs to the locally integrable function space, and it satisfies the following. It satisfies the following. So you have V prime. So sorry, you have W times V minus of, which is equal to V times V prime for every phi in the space of CC infinity functions, where CC infinity stands for all those functions. I have exhausted, let me use the symbol G, all those functions, real valued functions from omega to R, such that, of course, G is smooth. By smooth, I always mean infinitely differentiable, and G has a compact support. Okay. G has a compact support. That is the subset of omega where G doesn't vanish. Its closure is a compact set. So that's what I mean by a compact support. Okay, so smooth, compactly supported function. So if this happens, then I say that this W is the weak derivative of V. Okay, you see now this notion of definition does not have the pointwise definition of the derivatives. You don't have to define the quotient of V, that is Vx minus Va divided by x minus a and blah blah. Those sort of things have now been eliminated, and now it's defined via an integration by parts sort of formula. This is very much like the integration by parts formula. Okay, so this is what I mean by a weak derivative. Okay, so without losing much time, so let me just venture out to the problem in hand. Okay, so a suggested reading for people who are interested. Suggested reading for people who are interested can be a book by L.C. Evans, especially the chapter on L.C. Evans. The book name is probably PD. Okay, so you can read the chapter where it deals with distributions. Okay, distributions. It's not the distributions in statistics. Distributions in functional analysis means generalized functions. Okay, things which are not functions, but we still try to identify them with a function. Okay, so yeah, so let's get back to the problem. So what we do is, so we multiply this entire equation. We multiply this entire equation.
Excuse me, sir. Can
Yes,
I have?
yes.
Sir, actually, there is no chapter in distribution. I think you are referring to K7, or else
No.
if Evans,
No.
then
No, what I mean
Sobel of
is the
Space.
chapter. Yeah. What I meant is the chapter which consists the idea of distributions, where you have the idea of
Okay.
nullifiers and okay. So the chapter name is not distribution. Okay, so the chapter.
Yes.
Yeah, what I meant to say is which has distributions. Okay, so the
Okay.
chapter
Thank
name
you,
is
sir.
not distributions. Yeah. Thanks.
Okay.
Thanks. So multiply this entire equation by, let's say, a function phi, which is in W012. Okay, now it's a new notation. I have introduced you to W12, but now I'm introducing to what is called as W012. Okay, so let us first do that, do the multiplication business, and then let me explain what is W012 space. Okay. So let me just do this. Okay. I should actually not do with W012 because this is actually an incorrect thing to do. What I'll do is I'll multiply this with a function from CC infinity, because distributions cannot be multiplied in general. Okay, because the function's values could be you could land up in a situation where you have to multiply infinity into infinity, and you know that this is an undefined quantity. Okay, so multiplication of distributions is not permissible. Multiplication of two generalized functions is not permissible. Okay, so what I'll do is I'll first multiply with CC infinity. Okay, now before that, let me just give a brief of what is W012. It's the same thing as W12 except with one exception, that it consists of all those elements in W12 space whose boundary value vanishes. Now there is a word of caution. You cannot always restrict a measurable function on the boundary. Okay, you cannot always see. You can always restrict a continuous function on the boundary, but you cannot always restrict a measurable function to the boundary, because measurable functions could just be 0 on a set of measure 0. We still identify that to be a function, and boundary is always of measure 0. Okay, boundary, when you consider with it to be when you try to measure its the volume of a boundary, it's always 0, okay, with respect to the volumetric measure. So this is always not allowed. So I'll direct the readers to read what is called as the trace theory. Okay, read what is the trace theory. And again, I'll suggest the readers to the book by L.C. Evans. Okay, so it gives you an idea of how to restrict a function on the boundary, but in the process, you will lose a very surprising thing, and that is half a derivative. So in the price which you pay to restrict a function on the boundary is that you lose half derivative. Okay, you lose half a derivative, and this entire thing you can see in what is called as the trace theorem. Okay, trace theorem. So I have now multiplied this equation with phi. And the usual trick is to apply the integration by parts. The usual trick is now to apply the integration by parts. Okay, so you just try to integrate this guy out. Okay, it is still Riemann integration. I'm still in the Riemann integration process. I have not yet ventured into the Lebesgue integration process. So integration by parts gives this to be grad u dot grad phi equal to, this will be unchanged. So will this. Okay, there will be no changes in this. Okay, and this is true for every phi in CC infinity. Okay, this is true for every phi in CC infinity, because phi was arbitrarily chosen to multiply the entire equation. There is no boundary term involved after the integration by parts, because on the boundary the function is 0. It's a Dirichlet problem. So on the boundary it's 0. But then with respect to the norm, so this is again a passing remark. Again, it's a passing remark that with respect to the norm, with respect to the semi-norm rather, I should say, because this is actually not a norm. So with respect to the norm, this one, okay, with respect to this semi-norm, okay, so I'm just representing it with a modulus kind of symbol. Okay, so this is a semi-norm. Why is it a semi-norm? Because even if this is 0, v need not be 0. It could just be a constant, right? So it fails to be a norm. But however, it becomes a norm. It becomes a norm when you are dealing with a function in W012 space. With respect to the semi-norm, CC infinity closure is equal to W012. Okay, And again, here we have used what is called as the completion theorem. Okay, so not many things I have been doing all this while. It's only symbolic, is whatever I have written down is all symbolic, but there are two key things which I have used, namely the completion theorem and how am I applying the completion theorem. These are the only two things which has been used till now. Okay, so with respect to this norm, this semi-norm on this space, this becomes a norm because on the boundary you have 0. So okay, so it's on. So if something is 0 on the boundary, it has to be, and you know that the function is constant, then it has to be 0 in the interior also. So this semi-norm becomes a norm when you are dealing with W012 space, but it's not a norm when you are dealing with W12 space. Okay, fine. So now this is what we will call as the weak formulation of the problem. Why is it called a weak formulation? Because instead of solving the original problem, instead of solving this original problem, one will try to solve, one if tries to solve this integral equation and ends up getting a solution to it, then all you need is the function to have only derivatives of first order. You don't need a second order derivative. So it's a weak solution. So if you have a solution to this integral equation, then we will say that this solution which you have obtained is a weak solution to the given PDE. Okay. So if at all a solution exists, so therefore, if at all a solution exists, then it will be called a weak solution. Okay, fine. Now, so now we'll work with another basic trick. So imagine a high school student being given the problem of finding.
Excuse me. Excuse me one.
Yes.
So can I say the weak solution, if it is on a set of measure 0, can you say like that?
Yes.
No.
It is one kind of. It is one explanation of a weak solution. Yes. Absolutely. Yeah.
Okay. Thank you.
Yeah. Thank you. Yeah. So what I was saying is that if a high school student is given the problem of finding a root to this problem, okay, a linear equation with a non-zero. Well, these days high school students don't venture into these simple problems. So what one does is one may find out a corresponding functional. This is just one way of doing it. You find a corresponding functional to this equation, and then you try to find the critical points of G. So that will also be a solution to this problem, right? So when you differentiate and equate the derivative to 0, and then you look at the critical points, so basically it's solving this problem, right? So this is the basic trick which we are going to employ while attempting this PDE. So the role of Ax plus b, equal to 0 will be played by the PDE, by the given PDE, and the role of G will be played by what is called as the Euler-Lagrange energy functional. Okay, Euler-Lagrange energy functional. All right, it's called as Euler-Lagrange energy functional. So without venturing into a detailed proof of the energy functional to the given problem, I'm just giving you the energy functional to it. So the corresponding energy functional, our energy functional to the problem is as follows. So yeah. Okay, so we will take this energy functional and try to show that this has a critical point, a non-trivial critical point. So that's the job in hand now. Okay, so this is a functional. This is a nonlinear functional rather from W01 to R, and E is a C1 functional, okay, over the space of W012. Okay, E is a C1 functional where E prime U is a member of the dual of this space. Okay, the derivatives are always a member of the dual space. Okay, so we don't realize it in the multivariable calculus because in a finite dimensional space the dual is itself. So, but the difference comes when we are in an infinite dimensional space. Okay. All right. So this is what we have. So now let us venture out to establish the existence of a solution. Okay, so we try to establish the existence of a solution. So certain tools which we'll be requiring is the notion of Pallas-Male condition. Okay, Pallas-Male condition. All right. So a functional, this is a kind of compactness. Okay, this is a compactness condition. This is a compactness condition. I wish the talk was for 2 hours, which could have helped me to merge in several other details into this. But anyway, let me try to squeeze it further. So a functional I from I'll choose this to be a Banach space. A functional I from a Banach space to R, a functional rather, satisfies the PS condition. The PS condition if for every sequence in UN such that IUN goes to C and I prime UN goes to 0 in X prime, the dual of X, as n goes to infinity implies that there exists a subsequence of UN. I'll still denote it as UN. I'll not go for a notation like UNK or anything, such that UN goes to U. So this is some sort of compactness, right? So when you say what is one of the characterization of compactness? If every sequence has a convergent subsequence, right? So that's one of the characterization of something being the Bolzano stress kind of property. So this is something of that type, okay, with an additional condition of this one, the one which is within the braces, right? So the definition of compactness is always the same, namely every unit cover has a finite subcover, but it's only the characterization which changes as you change the spaces. Like for instance, you say something to be compact in a space of continuous function over compact set when the family of functions happens to be uniformly bounded, and in addition it also has to be equicontinuous. Okay, so that is when you can establish that it is having a convergent subsequence. So the characterizations changes from space to space, and this is what we have here. So this is some sort of compactness condition. So we will require this E to satisfy this PS condition. Okay, we'll require this E to satisfy the PS condition. So what we will show is that if this there is something called as a mountain pass theorem, okay, which is a bit geometrical by nature. Mountain pass theorem. So these two in combination will help us to establish the existence. Okay, so let me write down this mountain pass theorem, and yeah. So the idea is this. So if you're beginning at some point, let's say x0 in the space, let's consider this screen of yours which you're looking at to be your Banach space X, and there is a point x0 on it. Okay, and then if you can find out a ball around this point x0, okay, which is at a distance of r, okay, and if there is a point outside this x1, okay, so you have mountain ranges out surrounding this. Let's say you have, it's all surrounded by ranges, some mountain range. So you look for you look for all those paths, which moves from x0 to x1, of course under certain conditions. And if you can collect all those paths from here to here, okay, so you get some sort of this structure, okay. So you're having this kind of structure, okay. So then you can establish that there is a critical point to this energy functional, okay. So if you can cross the mountain, so there is some sort of this going up and coming down sort of structure. This is called as a mountain pass geometry. So the functional is said to have a mountain pass geometry. Then you can expect that there is a critical point to this energy functional. And exactly this is what our energy functional will possess, okay, energy functional will possess. But let me just write down the theorem formally. So suppose I from in Banach space to R, so X is my Banach space, okay. So because I'll be dealing with convergence, so I need a Banach space to work with, okay. Incomplete spaces are useless to me. Suppose I is a C1 functional, C1 is a must, okay. C1 is a must, is a C1 functional such that I of x0 and I of x1 is less than I of x for all norm x equal to R, okay. So values on this ball, value on this ball is greater than these two values, okay. And I obeys the PS condition, that is the Pallas-Male condition, which I have just now given, the compactness condition. Then I can say that I has a critical point. I has a critical point. And the critical value of that I is given by, infimum of all those paths. So gamma consists of all those paths from x0 to x1, continuous. Path itself means it's continuous, okay. And maximum of I of xi t, and t is in 0 to 1. Okay, so this itself says that this is a minimax problem. Okay, so this is a minimax problem. So basically, what sort of critical point does the mountain pass theorem gives? It gives you the saddle points. Okay, so it's like saying you get a structure like this. Okay, you get a structure like this. So you're here. You look at all those paths where you move to the other side of the mountain. Okay, you look at the other side of the mountain. So you look at its, you fix a path, then move from this place to this place, choose its maximum. You take this path, choose its maximum. You keep on choosing its maximum. Then you choose the minimum of these. So you get a saddle point kind of structure. So the critical point which you end up getting by the mountain pass theorem is actually the saddle point of the functional E. So, but what we all need is a critical point. We don't care whether it's a maxima, minima, or a saddle point, but all we need is a critical point for this problem to have a solution. Okay. So at this point,
you are minimizing the maximum ones, right?
Yes. That's right.
Oh,
that's right.
So first you are trying to find out the maximum ones. Then with all the supremum, you are finding out the minimum ones.
Exactly.
The
Exactly.
Okay.
Exactly.
Very good.
Okay. So what the detailing of this lecture will involve is that this functional satisfies the PS condition and the postulates of the mountain pass theorem, which will enable us to guarantee that E has a critical point. And by using our high school logic of finding out a root to a polynomial, we will guarantee that your original PDE has a solution. Okay, has a weak solution rather. Okay, so any questions at this point of time?
It looks very interesting. So please complete, sir. Let us see.
Okay, fine. Thanks.
Some more time is required.
Yes, absolutely.
Look pretty interesting.
Yes. Okay. I'll try to squeeze everything. So, but let's still see what I can reach.
Okay, you carry on, sir. It's okay. No problem.
Sure. So, firstly, the claim which I make is that E satisfies the PS condition. So if you don't remember what is a PS condition, just think it to be a compactness condition. Okay, some sort of compactness condition. Okay. Now the problem becomes more interesting. I mean, the approach which I'm going to use now will fail if my power, if the power of this exponent, becomes 5. Okay, that I'll discuss very soon. Okay, this trick which I'll be using now will work only up to the power being less than 5, not at 5. Okay, and above that. So let me just first show it for things which are relevant for powers up to 5. So, but anyway, I have chosen the power to be 2. Okay. So what do we need for showing that it's a Palace-Mail sequence? So let UN be a sequence in W12 such that, okay, let this, and I'll also choose a real number C such that E of UN goes to C and E prime UN goes to 0 in W012 omega dual. So this dual, for just your information, that this is denoted as W minus 1. Okay, fine. So we have these two postulates. So let us. So the question is, can we now produce a subsequence? Can we now produce a subsequence of UN such that UN goes to U strongly in W012. Okay, so subsequence and the sequence I am usually denoting by the same symbol. I am not using the symbol of UNK or UNL or whatever. Okay, so the moment I say subsequence, I'm still denoted by the mother sequence symbol. So you just have to understand that I'm just using the same symbol. I'm not changing the symbol. Okay, that's what will be our modus operandi now. Okay. So C, I can establish this as E of UN minus 1 by beta of E prime UN comma UN plus order of 1. Why? Because this means that as limit n goes to infinity, E of UN goes to C and E prime UN goes to 0, and that is why I have this order notation. Okay, I could have written limit n goes to infinity, C equal to this, but then I'm using this. This is a standard practice of doing it in PDEs. Okay. So what is E of UN? So let me write down the functional. It is equal to, the first term is nothing but the L2 norm of the gradient. The second term is lambda over 1/3 of UN cube. All right. And the third term has FUN dx. All right. And in addition, I have not said what is beta. This is still a mystery, even to me. Okay, so let's see what beta can be chosen. Okay, so this is going to be, so E prime U is going to be grad U dot grad phi minus lambda times U square phi minus mu times F phi. So this is, but phi is equal to U in this case. So this is just going to be this minus this quantity minus FUN. Okay, so what we have is half minus 1 by beta times this, alongside having lambda times 1 over beta minus 1/3 integral U cube, and then you have mu times 1 over beta minus 1. Okay, so from this, I'll demand that this guy is positive. So I'll choose beta to be greater than 2. And for this guy to be positive, I'll choose this to be less than 3. I can even choose equal to, in which case this will just vanish. I don't care. So choose beta to be this. Okay, and this term is negative. Okay, and this term is negative. This term is negative. Fine. So this is a positive term. This is a positive term. So I'll just caution you, this is a non-zero sequence. Okay. So in other words, I'll not demand this sequence to have infinite number of zero terms as well. Okay. So 0 has no importance. Finding out a trivial solution. Well, firstly, the problem which we are dealing with in this lecture is not having a trivial solution because f is non-zero for us. So, but even if you have a zero solution, it makes no sense. It's not a finding. Okay. It's like saying that I have found a set which is empty. So there's no point in that. So these two are positive numbers. So I can dominate this. I can majorize these two terms by the first term. Okay. So this is non-negative rather. So I'll just say this is this. And this guy, by the Holder's inequality, this is a negative term, so the thing will reverse. So what I'll be having is mu times 1 over beta minus 1 times norm of F2 into un of L2. Okay. So here I have used what is called as the Holder's inequality. Okay. Holder's inequality. This being negative, so I could dominate this. Now, further down, this guy, I'll just retain the first term. The second term, I'll further estimate this by what is called as the Poincare inequality by constant times f times L2. This is this one. Okay. This is this. Okay. So this is where I have used what is called as the Poincare inequality. Poincare inequality. It says that you have norm u square dx is less than or equal to c times norm u square for every u in W01 to omega. Okay, so that's the Poincare inequality. So in other words, it says that the space W012 is continuously embedded in the space L2. Okay. So I'll come to a brief introduction of embeddings, but let's first finish off this part. So now what does this say? This immediately says that UN is a bounded sequence in W. UN is a bounded sequence in W012. Why? Because suppose not, then this will have a convergent, this will have a divergent subsequence. Okay. So if I divide by norm gradient of norm UN square throughout, so this guy will go to 0. This guy will just be this term because then this will be cancelled out with this, and this guy will also go to 0. So that means you are arriving at a contradiction that 0 is greater than some positive quantity. Okay, so then this has to be a bounded sequence. And a property of reflexive Banach spaces says that if you have a bounded sequence, it will always have a weakly convergent subsequence. So this will have a subsequence which is weakly convergent. That is convergence in the weak topology. Okay, weakly convergent. That is UN weakly goes to U in W012. So the topology on this is now weak. It's not the norm topology. Okay, so this with respect to the weak topology, norm fails to be a continuous function. It becomes a weakly lower semi-continuous function. Okay, so what is a weak topology? It's the weakest topology on a space such that every member of the dual space is continuous. You look for the weakest topology possible to be given on a non-linear space so that its dual has all continuous functions. All right, so okay, so this weak topology you can refer to any standard book of functional analysis. Okay, you can find it in even BV-Limaye. All right, so this gives this, and now the job in hand is to show that this weak convergence is actually strongly convergent in W012. So that will establish that E satisfies Palais-Smell condition. So I'm not giving the detail of this part. So let's assume that this happens. What I'll leave the audience to relish upon is the following: that this functional actually has the mountain pass geometry. Okay. So what did I say? That you have a Banach space. You took a point here whose radius is r units, and if you can find a point here such that you can cross over this mountain paths around this boundary, then you can actually figure out having a saddle point here. So let me actually establish that this E actually has this mountain path geometry. E has, or E depicts the MP geometry or the mountain pass geometry. Okay, so I'll choose my x0 to be 0, okay, and x1 is to be found out, and r also is to be found out. Okay, so these are the three things which we need to find. So just give me 5 minutes extra so that I can just wrap up this one. So what is E of x0? E of 0, it is 0. Okay, E of 0 is 0. Now, if you look at the functional carefully, you have got this one minus this one, and then you have this quantity. Okay, so what I do is I majorize this by using our Poincaré and Holder's inequality. So here I'm using another embedding result. Okay, here I'm using another embedding result. So this I have not. Okay, and then you have C2, norm F2, and gradient of this. Okay, so here I have used what is called as the Poincaré inequality, and here I have used what is called as the continuous embedding of Sobel of space. Okay, fine. Now, if you choose mu greater than 0 to be small, how small? We'll just realize. Okay, how small should this be? It should be so small that this quantity. It should be so small that this quantity is positive. That is always possible by the Archimedean property of real numbers. Okay, so you can always choose mu to be small enough so that this quantity is positive, and then choose this r. So the norm of this one to be r small enough, r to be certainly less than 1, small enough such that this entire right hand side, the entire right hand side is positive. Okay, so you already chose this to be positive. So this is my radius. Okay, so I'll collect all those u whose L2 norm of the gradient is equal to r. You can see that this is greater than 0. Okay, so this implies that E of u is greater than 0 for every u in W012 such that norm of grad u 2 is equal to r. Now, fix an u in the ball, not in that way, fix an u such that u norm of u or gradient u is equal to r, any u. Let me give a name to this u naught. Okay, and consider E of tu. Consider E of tu. So what do you get? T to be a positive real number. So you just get t square by 2 E of tu naught. This is square, and then you have t cube lambda by 3. Then you have u naught cube minus t mu f u naught. Okay. Now, as t goes to infinity, this guy goes to minus infinity because t cube is the dominating term here. Okay. So what you find is that at 0, the value was 0. Around this, the value rose to, for every value you had it to be greater than 0, and there is some t after which this will become negative. So you have a mountain pass kind of structure. E has a mountain pass kind of structure. So as it goes to minus infinity, that implies there exists some t naught greater than 1 such that E of t naught u naught is less than 0. So this t naught u naught will be my choice of x1. Okay. So now let me fill in this blanks. This is going to be some t naught u naught. Okay. And this r also we have found out. Okay, so this basically said that if you have, I just could find out a ball around the origin in such a way that origin plays the role of the first point, x1 plays the role of the second point, and then you have this geometry where you can cross over the mountain. Okay, you can cross over the mountain. So E has a mountain pass geometry, E satisfies the Palais-Smell condition, and that will establish the existence of a critical point. Okay, so that's the proof in a nutshell. Okay, so maybe I cannot continue with the Poisson equation, so I'll probably wrap up here. Thank you.
Thank you, Dr. Choudhuri. If there is any question, please ask the speaker.
Thank you, sir, for your beautiful presentation.
Thank you.
Am I audible?
Okay. Yes, ma'am. You're audible. Thank you.
Okay. So, sir, in short, you have shown the existence of weak solution to a problem using the variational method.
That's right.
So I think the listener are eager to know what is the relation between weak solution and classical solution. If you can give some sort of relation between them, then
yeah. Thanks for your question. So the usual rule of thumb is that every classical solution is weak. Every classical solution is weak, but not conversely. But need not be conversely, rather. But need not be conversely. There is a deeper result which establishes this quoted sentence. Okay. The first one is that norm convergence, when you say something converges in a norm convergence implies weak convergence, but not conversely. Okay, but not conversely. Okay, for instance, if you look at the space of little L2, okay, the space of sequences where you have the space of sequences such that summation xn square is finite, okay, and then you look at the collection of sequences ENs where each EN consists of 1 at the nth point and 0 elsewhere, okay. This guy actually converges weakly to 0. Okay, this guy actually converges weakly to 0. Why? Because if you take, there is an inner product which can be defined on small L2. Okay, you know, we all know that it's a Hilbert space. So when you consider the inner product, and by the Riesz representation theorem, every functional of a Hilbert space has an inner product representation. So when I say something weakly goes to X, it means to say that Txn goes to Tx for every T in its dual space. Okay, so this is the definition of a weak convergence. Okay, so when I actually look at this quantity, so this has many terms in it. This has infinitely many terms. However, the only term of this one which will survive is the nth term. Okay, so that is xn comma nth term, and this goes to 0 as n goes to infinity because this is a convergent series. This is a convergent series, and the nth term has to go to 0. So rather, let me just use this notation. So this happens for every sequence. This happens for every sequence in L2. In other words, this happens for every member of the dual in L2, and this establishes that En goes weakly to 0. But En does not go strongly to 0. Why? Because the norm of En in the L2 space is always 1, but the norm of a 0 sequence is always 0. Okay, so the deeper sense in which this sentence can be understood is that it's all coming because of the topological property which is underlying in all the PDEs. Okay, so whatever PDEs we solve within inverted commas, the PDEs which we solve, we always try to find out the classical solution and using the strong convergence or the norm convergence. The moment you venture out into the weak convergence, the notion of weak convergence, you may fail to find a classical solution. You may. I'm not saying you will, but I'm saying you may. So this is the underlying property which actually establishes this sentence in the inverted commas. So as an example, if you carefully observe, if you just take this problem, okay, y double prime equal to your Dirac distribution. Okay, so this is a distribution. So delta naught is a functional from C naught infinity space to R, where it is defined as all action upon every element of C naught infinity is equal to phi of 0. Okay, or in other words, phi is sent to phi of 0. Phi maps to phi of 0. All right. So the function. So yeah. So the singularity is at 0. So I assume that 0 is in the domain. Okay. Now this problem has a free space solution, namely the mod x. Okay. Mod x with some constant, with some normalizing constant. This is a free space solution. Okay. This is a free space solution, and it's a weak solution. Why is it weak? Because this function is not even differentiable. Forget about it being twice differentiable. Okay, so this is an example of a weak solution which is not classical. Okay, and this does not have a classical solution. That's a different thing. Okay, but this does. So that's how I can give a quick reference to what a weak solution might look like. So
Thank you so much.
Does it answer to your query?
Yes.
Oh, thank you.
Some weak solutions may be classical.
Some weak solution may be classical, and that requires some regularity theories to use. Yes, that's right. But there are certain problems. But let me also add to your comment, which is very important at this juncture, that if you find a weak solution as an analyst, what we try to do is we try to see what is the best regularity or what is the best smoothness a weak solution can achieve. Okay, so even if we can achieve the solution, firstly we try to show whether the solution, the function is bounded or in L infinity, then we just raise our bar. Then we try to see whether it is at least Holder continuous or not. Then we try to check whether it is C1 or not. Then we just go to see whether it is C1 alpha or not. But usually C2 with very difficulty with whatever the problems which we have solved, we haven't come across a weak solution which can reach up to the regularity of C2, except when we have the Laplacian in picture. We also have problems where we use P Laplacians. Okay, the P Laplacians, okay, which is defined as the divergence of this quantity. So when you can observe that when P is 2, you just get back your Laplacian. Okay, so in this case, even for a simple problem like this, where f is in, let's say, L2 and u on the boundary is 0, the best regularity of a weak solution can achieve is C1 alpha. Okay, so not C2. Okay, where alpha is between 0 and 1. Okay, so that's another branch of studying the PDEs. That's called as a regularity theory of PDEs. Yes, but that's a very valid question.
Sir, thank you for the wonderful lecture. Sir, I have not just a question, it's a query. Any particular form of this phi means phi, something like Green's function?
Yes. They are basically, you mean to say phi of which one? These phis or?
This, if I solving something like y double dash equal to the Dirac delta function, if I choose this phi equal to some Green function and use the Green's identity, can I get the weak derivative of this function?
Yes, absolutely. This is actually the Green's function of this problem. You have rightly pointed out. Okay, so this mod x is actually the Green's function.
Okay, sir.
Okay.
Thank you.
Thank you.
So, any more questions from the audience?
Actually, this one looks pretty interesting to me. It's actually, I'm not done with 1 hour class actually.
Yes, that's an issue because this itself is a 2-semester course. So it requires a bit more, like it actually requires a series of lectures to finish.
Exactly.
Yeah.
Because there's so many things. I want to know what is a lower semi-continuous.
Right.
All these things. And so one thing, every
Yes.
bounded sequence has at least one subsequence convergence to subsequence, something like this, or what? What is that?
That is true in a compact set. When you have a compact set, that is always true. That is not true in general. For instance, you take the real line. Suppose you take the real line, which is non-compact, and take the natural number set. This is a sequence which has no convergent subsequence. So, yeah. So compactness is a key word there for this to hold.
So it is really nice. Thank you very much, actually.
Thank you, sir. Thank you very much. Thank you.
Thank you, sir. Any more questions from the audience?
Sir, am I audible?
Yes.
Okay.
Please. Yeah.
So in your first problem, you have taken f to be L2. So can you precise this result, like for how good function, like we will go for classical solution, or there exists continuous function also for which we cannot find the classical solution?
See, right now, what comes to my mind is that the best I can say is a smooth function. Okay, so nothing is better than a smooth function. Okay, so but then so if you take f to be L1, then probably even weak solutions may also fail to exist.
Yes, true.
Okay, so
I'm
if
asking,
I
like,
reduce,
we can take more regular function than L2 also, for which we cannot find the classical solution yet.
Yes, certainly we can. Continuity can also lead to that. Yes, f could be continuous also, for which that may happen. Yes.
Oh, thank you.
Is that what you're asking?
Yes, true. Thank you, sir.
Yeah. But L2 is a much wider class of functions which we have considered. So, yeah, but well, if you have a continuous function which is like blowing up at the boundary, you may even fail to have a weak solution. So that's more precise answer than my previous one. Okay, so if you have a continuous function which is just blowing up at the boundary, okay, blowing up in the sense which is going to infinity near the boundary. For instance, something like 1 over x, which blows up at 0. Suppose I take the domain as 0, open 0, 1, so which keeps on blowing up at the boundary. So such kind of functions may disallow such a thing to happen. Okay.
Correct.
Thank you.
Because
sir.
if you because if you note that the last integral f times u, if this exists, then I can proceed on with the proceedings. Okay, but if the integral f times u becomes non-integrable, which happens when f is a continuous function which is blowing up at some point at the boundary, then you just fail to have a solution, even weak ones.
Yes, sir.
Okay,
Absolutely.
so what we do is that we have bound. So if you choose the continuous function to be bounded, then you are almost certain to have a weak solution.
Yes.
Okay.
Yeah, it has to be bounded.
Yes.
Correct.
Right.
Any more questions from the audience? If there is no more questions, let us thank the speaker.
Thank you, everyone, for your patience and the invitation and the initiative which you have taken.
Thank you. So once again, we thank you, Dr. Choudhuri, for such a nice talk. This is the first talk on the first SOA weekly academic lecture. So I'm sure that the talk has enriched our knowledge knowledge and has shown an integration of one field to another field in mathematics, like function analysis to partial differential equations. And our thanks are due to the colleagues, scholars, and our students in the audience. And our big thanks goes to Dr. Manoj Ranjan Nayak, the Honorable President of Siksha Anusandhan deemed to be university, who have been always an source of inspiration to all of us. And I extend our sincere thanks to Professor Manjula Das, Madam, the head of Center for Applied Mathematics and Computing, and Dr. Apul Dev, one of our senior colleagues who have been wholeheartedly supporting us in conducting this SOAWAL webinar. Lastly, on behalf of Computer Center for Applied Mathematics and Computing, Siksha Anusandhan University, extend our heartfelt thanks to all. So, consider this as my vote of thanks. Anyone, HOD Madam,
Yeah.
do you want to say something?
Yeah. Thank you, Dr. Debajyoti Choudhuri. Really, we enjoyed your talk in this topic, and I think all my colleagues also would have enjoyed equally. So thank you so much, and in future also we can take the help of yours in this topic, if you don't mind.
Pleasure.
Yeah.
Pleasure.
Thank you, Dr.
Pleasure.
Choudhuri. Thank you.
Thank you.
Thank you, dear colleagues. Thank you.
Thank you very much.
Thank you, ma'am. Thank you all colleagues and students and scholars.
Soumya.
Okay, thank you. Let's stop recording, okay?
Yes, ma'am.